Welcome back to Python. Today we're going to be talking about sentiment analysis. So when we say sentiment, what we're talking about is somebody's attitude towards a situation or an event. So we're really talking about feelings. And the reason that we might be interested in sentiment analysis is for the use in business. So sentiment analysis is basically opinion mining. So if we are interested in how somebody feels about your business or about your product, we could take in their reviews. So we could ask them to review your product and rate it. And then we could mine that information and figure out how they truly feel about your product. So we could figure out if they have an overall feeling of positivity, negativity, or if they're just neutral on the product. And you may be asking yourself, why would we even be interested in this? Well, let's say that you're a new product on the market. Let's say you're a new smartphone and you're competing with the biggest companies in the world like Samsung or Google or Apple. You want to figure out where to put your money. Okay, so you got to figure out really quickly if your product is viable or not, or else you're going to end up running out of money. And to do that, you might potentially offer free samples of the phone. So you might give free phones out to influencers, or you might give them at a discounted rate in exchange for somebody reviewing your product. And you'll also host small groups to have people trial the product before you even launch it. Well, when you solicit the reviews from those individuals, and after they've tried your product, they're going to rate your product and also write some text about your product. So give you a review of the product. You can then put that text through a natural language processing system to conduct a sentiment analysis to determine their true feelings about the product. So you can tell if they have a positive feeling, a negative feeling, or if they're neutral on it. And by doing this, you're basically using your customers' feedback to determine how they feel overall about your product and to determine what they might not be telling you in person about the product. Now, sentiment analysis is a very new field within machine learning. However, it is a subfield of natural language processing, which is one of the big fields in machine learning and artificial intelligence. So things like ChatGPT, predictive text on Word documents or in emails, predictive text in your texting, all of those kind of products are based on natural language processing. So this is just a subfield within that well-developed field of natural language processing. And today we're going to talk about three different types of natural language processing. So we're going to start with machine learning and deep learning. And machine learning and deep learning are things that we've talked about previously in this semester and we've worked with previously in this semester, but we're going to use a slightly different approach here. So when we're conducting sentiment analysis for machine learning, basically what we do is take our text or our input text and then we pre-process that text. So in our case, we're going to be tokenizing that text. And what tokenization does is basically takes your sentence, like right here, we see this is the first step in the NLP pipeline, natural language processing pipeline. And that tokenizes it or cuts it up based on some kind of parameter like white space or commas or stop words. And stop words would just be words that don't really have meaning or value to the sentence. So they're not giving you any indication of the feeling in the sentence. And so it breaks up the sentence and then puts each of those individual words into its own box and turns it into its own item. So when we tokenize something, we basically are breaking it apart into individual entities. So that's our pre-processing stage. After we pre-process the data, we can extract features from the data. So we can count the data or count the total number of words. We also can encode the data. Then we can model the data using probability or statistical analysis. After we've modeled the data, we then are ready to get an output out of it. So we're ready to figure out what the sentiment towards that product or item is, and that'll either return positive, negative, or neutral. Now, in the case of deep learning, we have a very similar process or pipeline here. The big difference is in machine learning, we're using modeling. So we're using statistics and mathematics to figure out what the probability of the next word being this is, or what the probability of this sentence or tokenized characters means positive, negative, or neutral. In deep learning, though, we are abstracting our model quite a bit. So rather than using a model, a specific deterministic model to figure out what the feeling is towards these tokens or towards these characters, what we do instead is take the tokens after our pre-processing and then feed them into a dense layer in a neural network. And from that dense layer, we then feed them into two hidden layers. In our case, we'll be using LSTM or long short-term memory. So it'll go through one LSTM layer, then a second LSTM layer. And then after the second LSTM layer, we're ready to produce an output from it. Once we get the output, then we can determine if that is a positive, negative, or neutral output. Now, while deep learning is more abstract and we actually quite literally do not 100% understand what happens in the hidden layers of a deep learning neural network. What we do know is that deep learning is capable of catching very finite details within the tokens. So within the characteristics of the tokens or the vector that you're passing into your neural network, you can catch more specific information and features that a normal model would not catch, or that the human eye would not catch. And so that's typically why we've leaned towards deep learning for more intense or complicated applications. Now, in recent years, we've had a third type of architecture for machine learning and artificial intelligence come into play. And this type of architecture is called a transformer. Now, a transformer builds on deep learning models, but what changes is that instead of having to use LSTM, long short-term memory, in our model and use that as one of our hidden layers, the transformer actually incorporates a self-attention model. So attention in neural networks is the same as our attention, or that is the goal of it, is to be the same as human cognition and human attention. This basically allows the model to remember every single piece of text that you've handed it and place it in its memory, because each piece of text is encoded in a specific position. So rather than just being based on probabilities of your model, the self-attention or the attention mechanism in transformers lets you draw on any previous piece of data within the transformer, or that's been passed to the transformer, and any state within the previous states of the transformer. So essentially it remembers everything and every token you've ever given it, and based on all of that knowledge, it can predict the probability that this word will appear after that word, or so on and so forth, because it has previous experience and it has memory of that knowledge at every position in possible time. Now, we will not be building one of these transformers today. That is a very advanced application. There are good tutorials online about this. For instance, I'd recommend Andre Karpathy's video on building ChatGPT, or GPT, which is the general processing transformer. I believe it's a 2 or 3 hour tutorial on how to build a transformer. But what we are going to do today is actually access a pre-trained transformer model. So there's a giant website online called Hugging Face. And if you're not familiar with Hugging Face, basically the objective is to provide an open source repository for datasets, pre-trained machine learning and AI models, and also pre-trained applications that use ML and AI models. And in most cases, you can take a pre-trained model and access it with an API or even a module, or a package, excuse me, and then build your own apps on top of this module. And all of that information is found on the Hugging Face documents page, and they have basic implementations and examples of how you can do different things with Hugging Face. Now, if you do use a bunch of different models, or you are accessing a lot of different models and building on a lot of models, they do charge for that, for access to the API. But for basic users, you do have just general access to models in here. And so what we're going to do today is access a pre-trained sentiment analysis model on the Hugging Face website. And this pre-trained model is going to be based on BERT. And BERT is the bidirectional encoding representation transformer model. So this is a model that has been open and accessible for quite a few years now, at least 5 or 6 years now, and is basically trained on the Toronto book corpus and also Wikipedia. And it basically uses all of the information it gained from those resources to basically join text and build sentences and write sentences just based on its previous knowledge and its previous memory. So BERT is a precursor to things like ChatGPT. ChatGPT is not built on BERT, but the concept is the same. This is a general processing transformer that is capable of predictive text and also writing replies and conversation back and forth between you. So BERT can do many, many things without really much training. It's a pre-trained model that has a lot of experience, probably literally billions of data points worth of experience now, and there have been other iterations on top of BERT. So the iteration we're going to be working with today is called Roberta, and Roberta is a robustly optimized BERT pre-training approach. So Roberta was developed just a couple years ago. It looks like in 2019, so 4 years ago. And Roberta is based on BERT, but they improve on BERT by specifically hyperparameterizing and increasing the training dataset size of BERT to increase the efficiency of BERT. So what we'll be working on today is this specific model right here, where they took a bunch of tweets off of Twitter and accessed it through the API, and then used the Roberta model to train a sentiment analysis model. So they they used the basic NLP general processing transformer of BERT, built on BERT, into Roberta, and then from Roberta they trained Roberta on Twitter and on tweets. So while Twitter may seem like an odd use case for Roberta or for these pre-trained models, all Twitter is a text-based town hall or text-based thread application. So they can go in there and extract a bunch of tweets and scrape all the data or access all the data from the API and save it and then pass that to Roberta for Roberta to learn positive, negative, neutral emotion from tweets. And so Roberta was trained on approximately 58 million tweets and then fine-tuned for sentiment analysis with the tweet eval benchmark. And tweet eval is a specific paper that they published here. So in our application, what we're going to do is use this pre-trained transformer to predict the sentiment someone is feeling towards a certain set of text. And so we can do this pretty simply. To access the Hugging Face transformers, all we have to do is import the transformers package. So we're going to say pip install transformers. After we've installed the transformers package, we're going to say from transformers import auto model for sequence classification. That does exactly what it says, auto modeling and sequence classification of text. After that, we'll import from transformers the TF auto model for sequence classification. TF in this case is standing for TensorFlow, so this package is built on top of TensorFlow. After that, we'll import auto tokenizer. Auto tokenizer basically takes the text and uses a set of predefined rules to tokenize sentences that are passed to it. So instead of having to define each rule and each situation on how to handle text, like for instance on Twitter, someone's username may be included in the text, or there may be a bunch of dots in the text, or there might be white space or reference to an image. All of those things would typically require you to write a rule for each of them. Instead of having to do that, in this case, you can just pass it to auto tokenizer and it'll automatically remove it and figure out which of the information in that tweet is important. After that, we'll just import NumPy to deal with our arrays, then SciPy to give us our probability distributions, then CSV to import CSVs, and URLlib to make a request to the Hugging Face website. Now that we have all of our packages imported, what we're going to do is define how to pre-process our text. So we're going to define stage 1 of our image here. So we want to pre-process and tokenize our text that we'll be passing to the model. Now in our function here, pre-process text, what we're going to say is make a new list that's called new text. New text will basically contain all of our vectors or all of our tokens for passing to our transformer. And then with that new text item, what we're going to do is say for t in text.split, and the text.split is just going to be whatever text we've passed to the pre-process function. For t, we're going to say t is equal to @user if it starts with the @ sign. So again, dealing with the @ symbol in our tweets, and if the length is greater than 1. So you can't just have the @ symbol. There has to be something beyond the @ symbol. After that, we're going to say t is equal to HTTP if t starts with HTTP, else t. So this is basically handling any website information that may be in our text. Otherwise, the auto tokenizer can handle all of the other information. So with that, we say for t in text.split, we handle this specific information. Then we're going to take our text and append it to our new text item that we created above. And then we say return blank space dot join the new text. So join all of the tokens from the new text into a single item that we will now return as an output. Now, within the Roberta Twitter base package, there are different modules that they've built in. So they have modules for emojis, emotions, hate, irony, offense, and sentiment. And they also have different stances that are built into the package. In our case, we just want to do a basic sentiment analysis. So we're going to define the task of our Roberta model here as sentiment, so that we can analyze how somebody feels about our tweet. After that, we're going to define our model object, and model will be equal to the Twitter Roberta base model, and then whatever task that you have assigned for the base model. So we'll draw on the task item from up above. Once we've defined the model, we can pass the model and the task information to the tokenizer. So we'll say that our tokenizer is equal to the auto tokenizer package dot from the pre-trained and then the model that we're interested in. So again, a reminder that the auto tokenizer and the pre-trained model here are both from the transformers package. So these are things that are built in to the Hugging Face transformer package or module. Now, once we've passed our tokenizer or created our tokenizer object, we are going to download the label mapping. So we're going to create a new object that's called label, and then we have a link to the label mappings. These are basically sets of data sets related to whatever specific task that we've defined. In our case, sentiment is what we're interested in. And then within the sentiment data sets, they have mappings for what each word means and how to rate each word. So that's all predefined for you. So we will just grab that from the tweet eval package that we were just looking at. Now, with the mapping URL, what we say is with the URL lib.request of URL open, pass the mapping link, so pass this GitHub link, and we're going to say as f, and then we say HTML, read that link, decode it, split it up, and then read the CSVN for our data set, and then add the labels for each row in the CSV reader if the length of the row is greater than 1. So all we're doing here is taking this predefined data set of the mappings for each of the words in our sentiment analysis and reading them in as a CSV document, and then taking that CSV document and adding them to our labels object so that we can reference these labels in the future. So we will go ahead and run this. It shouldn't take very long. All it has to do is download all of this information that you've asked for and add it to your current runtime. And there we go, just like that, just a couple of seconds. So now what we can do, we've basically built all of the framework that we need out of the Transformers package available on the Hugging Face website. We've also downloaded our specific mappings for our data set and saved them as an object that we call our labels. Now what we're going to do is actually define our model. So we're going to say that our model is equal to the auto model for sequence classification. So that's a built-in model in the Transformers package, and we're going to say from the pre-trained model, which is our model that we defined up above as the Roberta Twitter base model with our specific task, which is sentiment. So we're going to take that model, pass it to the auto model for sequence classification, and save that as our overall model. Now from our overall model, we're going to say save the pre-trained model as our model. Now once you have your pre-trained model saved as the model object, you can pass some kind of piece of text to your model. In our instance, we're going to say good night with the smiley face, and then with that text, what we're going to do is say pre-process that text. So based on this function we set up above, where we are basically parsing the information and looking for exceptions like @users or website information, we're going to parse that data and then save it again as the text object. So we're going to iterate over that object. Now, based on that text data, we are going to tokenize that data with the built-in tokenizer from the Transformers package, and then we're going to encode our input. With our encoded input, we're going to pass that encoded input to our model and then save that as our output. And then based off of the output, we are going to detach and save the data from the output that was passed to our model as a NumPy array, and that NumPy array will be equal to the scores. So once we take our encoded input and passed it to the model function from up above and saved that as our output, we get a score back for each of the words in our input or in our text. And then based off of those scores, we use a softmax probability function to calculate the overall score, the probability of that score, and then save that score as our final output. Now that we have our scores from our output, we're going to take that array of scores and sort them and save that as our ranking. Once we've sorted them from lowest to highest, we're going to inverse the ranking and basically put the highest at the top and then reiterate over our variable and save it as the ranking. And then we're going to say for I in the range of our scores, so basically iterate through this entire NumPy array, and we want you to take the labels object that we created earlier, which has the basic mapping for the data set for our labels for sentiment analysis, and we want you to compare the rankings of our labels and the scores of our rankings and then print out the order of the values. So in our case, let's go ahead and run this and check how the model sorts and ranks our text here, which says good night with a smiley face. To us, obviously, that is a positive text, right? Good night, those words are kind of neutral, but the smiley face makes them positive. So we'd expect that this would be ranked as a positive piece of text. There we go. That's exactly what we see. We see that good night with a smiley face is ranked as the likelihood being 0.8466 as positive, 0.1458 as neutral, which, like I said, is kind of what I expected, right? Because good night without a smiley face doesn't really have much value behind it. It's likely just a general notice. And then lastly, we see that the likelihood that it's negative is 0.0076. So very, very low that this is a negative message. Now, what happens if we remove the smiley face off of here? How does it then rank our text? Now you'll see that once we remove the smiley face from our text here, the positive emotion here goes down from 0.85 to 0.58, the neutral goes up to 0.3751, and then the negative goes up just a little bit to 0.0353. So again, without the smiley face to convey emotion in that text, there's really not much information for it to go off of here, and it is kind of just a neutral piece of text. Now let's try something a little bit more obvious. So I'm going to erase this and say, I hate your guts. Now, I hate your guts. If you said something like that to a person in public, I think everyone around you would be appalled. They would be very, very scared or concerned that this was a serious situation because the word of hate is in there and you're referring to guts, which people don't typically think is like a positive, or it doesn't evoke a positive emotion in a person. So let's see how it ranks this text. And again, I'm expecting it to be negative. And there we go. So I hate your guts is showing a negative emotion of likelihood of negative emotion of 0.9697. So almost 100% chance that this is a negative piece of text. And then neutral is 0.02, and then positive likelihood is 0.0043. So extremely little. Let's try another positive one. Let's say I had the best day with you. And we'll, instead of a period here, we'll include an exclamation. And again, we'd expect this to be positive because it said I have a great day with you. To a normal person, that would be positive output. And you see that's what the model predicts too. It says the likelihood that this is positive is 0.9908, neutral likelihood is 0.0074, and then negative likelihood is 0.0018. So this is a perfect example of how if you were a business and you were accepting reviews from your customers, you could analyze each of your reviews, pass it to this pre-trained transformer, and determine how your customers truly feel about your product. So it allows you to read between the lines and determine if they really liked it or if they were negative about it. And even though it doesn't provide you a very in-depth look, it's not saying these are what your customer suggested, it does give you overall emotion. And as I said, there are other sub-modules within the Transformers module to look for other potential interests. So you can look for emotion, you can look for hate, you can look for someone being offended, and then again sentiment. So this is a great example of how you can use this for business applications. It's also free and open source, and so you can play around with this and build your own application, and also build your own pipeline. So based off of this pre-built transformer, you could pass that to an application, and every time you get a review on your product, it takes that review on your product and then scores it, and then every day you get an email of 90% of your product review yesterday were positive and 10% were negative, or however you want to handle it. So this is just a part of your pipeline to then build on top of. Now, let's say you want to conduct your own sentiment analysis. What would you do then? Well, in the case of machine learning or deep learning, it would be similar to what we've done before. Okay, so we're going to have to create this pipeline ourselves. So we're going to take some input text, we're going to pre-process it and turn it into tokens. We're going to extract information from it, model it, and then determine if it's positive or negative. And with the deep learning, we'll build a neural network with hidden layers, a dense layer, and encoding. So in our instance, let's say that we want to, again, work with Twitter data. There's a free Twitter data set on Kaggle here. It's 1.6 million tweets. And basically in this data set, they have a bunch of different content. So it gives you the target values. So the tweets are all ranked on a scale of 0 to 4, with 0 being negative, less than 2 being negative, 2 being exactly neutral, and then greater than 2 being positive. It has the IDs of the tweet, the date the tweet was written, the username, and then the text. So let's say you download this data set and you want to use it to conduct your own sentiment analysis. Well, to do that would actually not be that challenging. First thing we're going to do here is import pandas as PD. If you're not familiar with pandas, go check out one of my earlier videos on data manipulation. Once you have pandas imported, what you're going to do is call on pd.readCSV. So you're basically importing your data set as a CSV. You're then going to tell it the location of your file, and if your data set has headers, In this specific data set, there actually is not or are not any headers. So after we say no headers, what I say is names, and then you can add headers to each of your columns in your data set, and then you specify the encoding. Because we are dealing with tweets here, and tweets again can contain the @ symbol or exclamation points or other weird or strange non-normal characteristics, we cannot use UTF-8 encoding. In our case, we'll use Latin-1 encoding. And we save all of that information as the data object in our workspace. Once we have that saved in, we can load the data object and just check that it read in correctly. And this is what our data looks like. So you'll see we've got the target values of how they were ranked right here. So ranked as zeros in this case. We've got the IDs of each of those values. We've got the date which they were written. This is kind of older data, 2009. The flag, you don't really have to worry about that in our case. We wouldn't be using any of that information. The user, that's just the username. Again, doesn't really matter. So immediately you could delete the flag and the user ID, and then you have your text column. Your text column is with all the information that we're actually interested in. So we've got our data read in. We know that it's in a format that we're interested in. There's a couple of things that we could clean up, but overall you could leave it in this format and still conduct your sentiment analysis. Once you have your data imported, we're ready to pre-process our data. In our case, we're going to be pre-processing our data to remove any of our unwanted characters, and then to tokenize our text into individual words. And to do that, we'll be using a Python package called NLTK. And NLTK just stands for Natural Language Toolkit. This is an NLP or Natural Language Processing Toolkit designed specifically for. And so once we have that downloaded, what we'll do is import NLTK. Then we'll also import NLTK.tokenize, so the sub package, and we'll import the word tokenization package. And then we're going to say NLTK.corpus. Corpus is basically a subset of packages that has specific words in them. So in our case, we're going to import the stop words. And then lastly, we'll import RE. And RE is the Python regular expression package. This is just to help with the overall processing of the data and to allow you to use shortcuts in your programming or in your writing of your code. Now, once we have all of our package imported, what we're going to do is take the NLTK package, and then we're going to download the punked words, and then we're also going to download the stopped words. The punked words or punked subpackage is part of the word tokenizer subpackage. This is basically a unsupervised machine learning model, pre-trained machine learning model that is used to separate text based off of specific requirements or rules. And then the stop words is a package that allows us to pick out words that are not useful. So words like a, and, or but, or is, things that may not be providing meaning to the sentence or to that specific vector or array that you might just want to cut out in certain situations. Once we have those two subpackages downloaded, what we're going to do is define our preprocessed text function again, just like we did up above. And in this case, we have more rules that we need to throw in here. So first off, we're going to define our text that we passed in, and we're going to say text is equal to text.lower. So we're going to take all the information from our text, and we're going to turn it all lowercase. Then once we've done that, we're going to take the RE or regular expression package and use the subpackage to take any non-normal characteristics or non-alphanumeric characteristics, so nothing that's A through Z or 1 through 9, and then we're going to pass in just blank space into the text, and we're going to pass it the text object. So for instance, again, in a tweet, we might have an @ symbol. An @ symbol is not an alphanumeric character. It's also not a word that provides value necessarily. It's just a username when we're talking about Twitter. So in this instance, we might want to remove those @ symbols, and we can do that using the RE package here. And then we iterate over the text object again to resave it as text. Once we've created the text object, then we're going to use the word tokenize package in NLTK and create tokens out of our text. And we're going to say token for token in tokens. So for each of the different words or objects in our array, for each token in the tokens object, if it is not a token in the stopwords.words, then we want to save it as a token. So while that's confusing, this is just a condensed down version, and basically says take the tokens object that we created up above, look for any of the stop words in our words in that token object, and if it is not a token as what we have predefined up above, I want you to remove it. If it is a token that has been predefined up above, I want you to save it as a token and then iterate all of those onto the tokens object again. And then at the end of that, we just return the joined tokens back from our preprocessed text module. from our preprocessed text object. Now, after we are done writing our pre-processing function, what we're going to do is take the data object we created up above with our text column, and we're going to say dot apply the pre-processed text function. So we're basically taking all of the data from our 1.6 million tweets in the text column and applying the pre-processed text function. From that pre-processed text function, we're going to save this again as a data frame or df object that has a column called text. After we've created that object, we can then just simply check to make sure that we've updated the data frame here. So now we're done with all of the processing of our data, and we can actually prepare to split and train our data. So in our case, we've used this function before. We're going to use scikit-learn's train test split module. And so what we need to do here is tell it where it's finding its text, as well as where it's grabbing its labels for that text. So what is the data we want to train on, and what are the labels or rating systems that we're using to train that data, or to train this model, excuse me. So in our case, we're going to take our text object again, and we're going to set that equal to the D of text for D in data, so for that data object from up above. And then we're also going to say that in the data object, we want to take the target column, which is the column that has the ratings for each of our tweets, and we want to save that as the labels. So the text is the material that it's studying, the labels is the rating for that material. And then what we're going to do is create new objects, one that's called train text, one that's called test text, then train labels and test labels, and we're going to pass that through the train test split algorithm from the scikit-learn package, and we're going to pass it the text and the labels, and we're going to say our testing size is 0.2 or 20% of the data, so we'll be using 80% to train and 20% to test, and then our random state to be able to pull on this information again is set at 42. Now that we have our data split, we can actually train our module. In our case, we're going to be using a count vectorizer and then the multinomial NB or naive Bayes to actually produce a simple naive Bayes classifier. So first thing we're going to do is import that count vectorizer. All it does is take your tokens that you've produced up above and determine how many times that token is occurring across your entire data set, and then calculating probabilities or calculating and extracting features, out of your data set based on the count found in your data set. Now the multinomial NB or multinomial naive Bayes, so this is taking a multinomial approach to assigning a probability to each of the words showing up in your text. So for example, the NB naive Bayes is based on Bayes' theorem, and it assumes that each of the words found in your data set is independent of every other word. So it's using a multinomial approach to assign each of those words into the different classes in your pipeline. So in our example, positive, negative, or neutral. Now what we're going to do is instantiate an object called text_clf, and text_clf is basically just going to represent our pipeline that we're building here. So our pipeline of interest is using our count vectorizer and then our multinomial NB, and we are passing those objects into our pipeline and then saving those parameters as the text_clf. Now, based on the pipeline that we just formed as text_clf, what we're going to do is fit our data onto the text_clf. So we're going to say text_clf.fit, and then we're going to pass it the training text as well as the training label. And what that'll do is train our model, or train it on our data set using the naive Bayes classifier to fit into the classes that we've defined, so positive, negative, or neutral. After we've trained our model, we then are going to evaluate the performance of our model. And so we're going to use the sklearn metrics, scikit-learn metrics, and the accuracy score. And what we're going to say is that based off of the text_clf pipeline that we created, I want you to predict based off of these test texts, so the 20% of our data that we set aside to test on, I want you to predict what the labels of that data would be. And then I want you to use the accuracy score metric from scikit-learn to determine the accuracy of our test labels in comparison to our predicted labels and tell us what the accuracy is. Now, once you finish evaluating the performance of your model, you can start to test on new data. So to use this model and make predictions on this model, what you have to do is pass the new text from your environment into the model. So we're going to create a new object that says, that's called our new review, and this new review will be equal to, this restaurant was amazing. The food was delicious and the service was excellent. After you have that new text created and that new review created, you can then pass that information to the text CLF pipeline and use the predict function to analyze that new review and then predict the label for that. And what we're going to say is that if the predicted label is greater than 2, we want you to return that it's a positive sentiment. And we're going to say elif, or if any other condition occurs and the predicted label is less than 2, then I want you to return that it's a negative sentiment. And then else, just return that it's neutral. So if it's just exactly 2, we want it to be labeled as neutral. And that's how you can create your own machine learning model for sentiment analysis for your business or your reviews or whatever it is that you want to use this information for. For example, another application that I just thought of, you could use sentiment analysis for politics. So if you don't believe the true emotion that's being shown in the text in a news article or something about a political event, you could pass that text into your sentiment analyzer and your sentiment pipeline and determine if that truly is a positive emotion or negative emotion based on what the host said or what the article says. Now, the other option here is to use a deep learning sentiment analysis instead of a machine learning sentiment analysis. So again, rather than using statistical models like naive Bayes, what we're going to do is create a neural network, and this neural network should be capable of catching more of the nuanced features that are found in our data set. So again, we'll be working with that Twitter data, and so you can download that data again from Kaggle. Once you have that data downloaded, we're going to import it the exact same way that we did before. So we're going to import pandas as PD, and then we're going to read the data set in as pandas with read CSV, and we'll save it as DF. Once we have the data set loaded in, we can pre-process the data. We're going to use a similar format to what we did last time with a couple of extra settings that we're going to. So again, we'll be using NLTK and RE for regular expressions, and we're going to use our stop words here. Next, we're going to download our stop words, and then we're going to pre-process our text again. Again, we're going to make sure all of our text is lowercase. We're going to remove any special characters and punctuation. We'll remove our stop words that we're not interested in. We'll then split the text into words, and we'll say for words in the words, if not in our stop words that we created up above. We want you to take that W or take that singular word and save it over our words object. We'll then join all those words back into a string and save it as our text, and then we'll ask for that text to be returned to us. Now, once we've defined that function, again, we're going to process our text. So we're going to say df of text, so that text column in our data. We now want that to be equal to the df of our text in the original data set, and then we want you to apply the pre-process of our text. Once we've iterated over the text column, we're then going to go in and tokenize all of our information for our tweets and convert them into unique integers. So from the TensorFlow package, we're going to import the tokenizer. What we're going to say is that the tokenizer is equal to the tokenizer function, and that the number of words the tokenizer can process is 5,000 at a time. Once we've defined our tokenizer object, we're going to take the tokenizer and we're going to fit it onto our text. So we're going to take our text and fit it to tokenizer, and all of that text is going to come from the data frame text column. Once we fit the tokenizer onto our text, we're going to convert the text to a sequence of integers. So we're going to take the tokenizer and use the text to sequences package in the tokenizer subpackage and pass all of our text to the text to sequences, and then we're going to save that as X. And X will be the value that we pass from our environment through our neural network to then figure out the numerical formatting, to figure out the sentiment behind our text. So now we've got our text side of things taken care of. We've got our sequences converted into the integers and a usable format. Now we need to encode our target variable, which in our case is the rating of our tweet. So if it's positive or negative or neutral. So what we're going to do is take our df target variable. We're going to apply this lambda sequence, and basically what this does is assigns either a 1 or a 0 to the sentiment or to your target variable based on your preset conditions. In our case, we're going to say that the lambda of x will be equal to 1 if x is greater than or equal to 2, so if it's positive. Otherwise, we're just going to set it as a 0. And then we'll save this in a column that we're going to call sentiments in our original data frame. And then with the data frame sentiment column, we're going to say data frame sentiment.values. Those will be equal to our y values for the data set. So now we've got our text converted to integers, values that we can use and pass to our neural network. And we've also encoded our target variable as a binary value of either 1 or 0. So we can now pass all of this into our model and actually start to build our neural network. And in our case, we're going to be building a long short-term memory neural network. So this network will be laid out exactly like what we talked about up above, where we preprocessed our data. That's what we just finished. And then we're going to take and pass it into a dense layer. From that dense layer, it'll go through 2 LSTM, long short-term memory layers, and then that'll be averaged using, I believe, a soft max probability, and we can then print out either positive or negative for our emotions. So what's unique about the long short-term memory is that it is the precursor to the transformer. So it remembers the last few items or words at a position in time and then encodes that information into the network so that you have some level of memory attached to your data set. So it's not as good as a transformer, but it's also easier to build than a transformer. And we've worked with these before. If you have not seen that lesson before, go to the machine learning part 2 and you can go through our deep learning tutorial with us. So let's go ahead and get started. So what we're going to do is import from TensorFlow the sequential package. Sequential package allows us to build our model sequentially. And then we're going to import the embedding, LSTM, dense, and dropout layers. The embedding basically embeds the data, so it builds on the data and positions it or encodes the positioning of it. The LSTM provides us the long short-term memory layers, just like what we need to build right here. The dense layer is a fully connected layer where all of the inputs are connected to all of the outputs. And then dropout is a function that basically allows you to make sure that you're not overfitting your data and also not underfitting. So you set a certain percentage of your points or your data points to be dropped out at random from your training. Let's go ahead and start defining some of our model architecture here. First off, the sequential function, and we're going to save that as our model. Once we've instantiated and turned on our model, what we're going to do is take the model and we're going to add an embedding layer. The embedding layer, it's going to take all of our inputs that we created up above for our text, where we converted them into integers, and then pass it into their neural network. So the embedding is basically that first layer of our data, or of our architecture. And in the embedding layer, we're going to expect 5,000 inputs, and we want it to condense that 5,000 inputs down into 128 different inputs. After the embedding layer, we're going to add another layer that'll be an LSTM, or a long short-term memory layer. From the long short-term memory layer, we're expecting 128 inputs, and of those 128, we want it to randomly drop out 0.2 or 20% of those inputs. And in this case, we're also going to add in a recurrent dropout. So in a recurrent neural network, because we're using long short-term memory and basically we're passing data from each time point to the next time point, or a certain certain percentage of that data to the next time point, we're creating noise in our data set. So recurrent dropout can delete some of that noise basically by just taking those values that were being passed to the next layer and setting them to 0. So we can reduce some of that noise and try to help optimize the model and reduce the overfitting of the model by adding a second dropout here. Now, for this LSTM layer, we're also going to add return sequences equal true, because we do want our sequences to be returned from this layer so that we can pass them from this LSTM layer into the second LSTM layer. And after that first LSTM layer, we add a second LSTM layer. In this case, because we had 128 the first time, that'll basically be cut in half. And in the second LSTM layer, we're going to be expecting 64 inputs. Again, we'll be using a 0.2 or 20% dropout for the regular dropout, and then for the recurrent layer dropout, we're also going to use a 20% dropout. Once we've gotten through the second LSTM layer, then we're going to add our last layer of our network, which will be a dense layer. So in the dense layer, all of our inputs are going to be connected to all of our outputs. So we're going to call on the dense function. We're going to want our units to equal 1. So from these 64 inputs, we want to go down to 1 possible unit coming out. And then we're going to specify the activation function for this dense layer. In our case, we'll be using sigmoid. The reason that we're using sigmoid is because up above, we converted all of our reviews or all of our ratings from a 0 to 4 scale into a binary scale of 1 or 0. So in this case, the sigmoid is returning that binary value out to us. It's going to give us either a 0 or 1. Now that we've defined our total model architecture, what we're going to do is compile that model. And so we'll compile the model by calling on model.compile. And within this compile function, what we're going to do is specify the loss function that we want to use. In our case, we're going to be using binary cross entropy. Binary cross entropy is a fancy word for log loss, and this is basically a way of predicting how close the probability is to the correct value or classification of that value. So in our case, we're either predicting a 0 or a 1 for binary classification, and so the closer the probability is to the correct measurement, the better the outcome of the model is, or the better fit the model is. And then as far as our optimizer for our model here, we will be using Atom with a learning rate of 0.001, and our metric for measurement of success is accuracy. The Atom optimizer is basically a stochastic gradient model that is trying to optimize your model. So it takes all of the weights compared to the losses and then optimizes the weights and the losses to try to parameterize your model and improve on your model and decrease the cost of training while improving the efficiency of your model. So put it simply, as you train more, you want the cost to decrease and over time, and you want the efficiency of the model to increase over time. So the log loss and the loss function here and the optimization model here, the Atom model, go hand in hand. You need both to be successful. Now that we've defined the total model architecture as well as compiled the model, what we can do is then train the model. So again, we're going to be using the train test split module or function from the scikit-learn model selection subpackage, and we are going to specify that we want to create xtrain, xtest, ytrain, and ytest. And those will be set based off of the train test split function, where we're going to pass the x, which is big X that we created up above to represent our text as integers, y, which is our binary of either 0 or 1 to represent positive or negative emotion. Test size, we're going to set to 0.2 or 20% again. So we're going to use 80% to train, 20% to test. And then we're going to set our random state equal to 42 in case we ever need to draw on these exact settings again. Once we've set our X and Y train and test sets, we're then going to train the model on our training set. So we're going to call on the model that we defined up above, and we're going to say model.fit, and then we need to pass it the X training data, the Y training data, tell it how many generations or epochs to train for. In our case, we're going to do 10. Then we also need to set the batch size, or how many possible inputs it can take in at once. In our case, we're going to say 64. And then lastly, we need to specify the validation data location, which will be xtest and ytest that we created up above. Once we've trained the model and fit the model, we can evaluate the model for loss and accuracy, and we can call on the model again. So we just say model.evaluate, and we're going to evaluate based on xtest and ytest, which are our validation data from up above. And what we're going to ask for in this case is actually loss and accuracy. So we want to look at the loss over time to see how it improved, or did it improve? Maybe it got worse over time. And then the accuracy, we want to see how accurate is this model at this point in time at predicting the label, so positive or negative, for our testing data. So that would be the end of forming and training your model. Obviously, after you evaluate the model, you then could hyperparameterize your model to improve the overall accuracy and efficiency and decrease your loss function. Or if you're satisfied with it, let's say you get 97 or 98% accuracy the first time around, then you can just start using the model to determine the sentiment behind some kind of text that is being passed into your model. So now what we're going to do is plan to make predictions on new sets of text. So similar to what we did last time, we could simply pass a new object that's just called text to our model and then predict the sentiment on it. Or we can take the total pipeline that we just produced up above for our deep learning model here, and we can create a new function out of it. So we can say define predict sentiment, and then we're going to tell it that we want it to pre-process the text that was passed into this model and then save it as text. So that's calling on the preprocess function from up above. And we're going to convert the text to a sequence of integers that we can then pass into our neural network, and we will save that as our sequence. And then we're going to pad the sequence to match the model input shape. So this is basically just using a built-in scikit-learn package or TensorFlow package, to take our sequence, determine the max length of that sequence, and then pass it out. So this is basically a pre-processing step. After we've passed it through the pre-processing step, what we're going to do is take our model that we created up above and say model.predict on this sequence, save that as our sentiment, and then return the sentiment to us. So this is just creating a process and a pattern for the computer to follow. So similarly, as we set up above, we could take each new review and pass it through a pipeline and determine the sentiment behind a review for your business. You can also create an entire function that does it all in one step for you by building on that pipeline. And that's what this predict sentiment function is going to do. So now each time that you receive a new set of text that represents the review of your business, you can just take that text object and pass it to the new function, predict sentiment, and then return the sentiment, and then print out that sentiment to determine how that person feels about your product or your restaurant or that political opinion, whatever it may be. And that's it. I know that seems like a lot of information, but we've already done machine learning and deep learning before, so we're building on our base there. Again, if you haven't seen those, go back and watch them. They were in, I believe, Lecture 5 and Lab 5. And then on top of that today, we also used a open access pre-trained model called Roberta to use a transformer architecture and determine somebody's sentiment around some words that we were saying. So I hope you guys really enjoyed this. I hope you enjoyed seeing this kind of interesting subfield that's developing in natural language processing. As always, like, comment, subscribe. I hope you have a wonderful day and even better rest of your week, and I'll see you next time.